Welcome to the AI Sherpa Podcast Deep Dive. I am so glad you could join us today for what I think is one of the most critical deep dives we've ever done. Our mission today is all about the future, a future where intelligence is, well, it's engineered. And because of that, ethics have to be hardwired right into the system. You've given us a really dense stack of sources, all focused on this radical convergence of artificial intelligence and synthetic biology. And we are going to pull out the absolute critical insights from that material for you, especially on how this combination is forcing us to rethink ethical design from the ground up.
That's exactly where the conversation is right now. It's the hot topic. When you
Wow.
look at the research, especially the stuff coming out in 2025, there's this central, almost provocative idea. It's the question that's driving everything. Can we actually engineer an AI system that doesn't just act smart, but has an innate moral compass?
An innate one, not just one it learned.
Exactly. We're talking about building in safeguards that are inspired by biology. Think of it like digital DNA, something that makes unethical behavior impossible by its very design, not just because of its training data.
Wow. That idea is the ultimate hook, isn't it? It suggests we're moving past just training AI to do good things and toward designing AI that fundamentally cannot do harm. And to get our heads around how we get there, we first need to appreciate just the sheer power of this convergence. We have two massive forces at play. So on one side, we've got synthetic biology. For anyone who's maybe just catching up, how should we be thinking about synbio in this context?
The best way to think about synbio is as applied engineering for life itself. It's about taking biological systems, DNA, proteins, cells, and applying classic engineering principles to them.
So things like standardization, modular parts.
Precisely. Standardization, modularity, getting a predictable function. We're designing and building new life forms or, radically redesigning existing ones with the kind of precision you'd use to design a circuit board.
Okay. And then the second force is, of course, artificial intelligence, which, as the sources all confirm, is accelerating this whole process of biological design at a speed that, it's unimaginable even 5 years ago.
It's not just a collaboration, is it? It's really a symbiotic relationship. One field is just turbocharging the other.
And the year 2025 is being flagged as the moment this becomes, and I'm quoting here, one of the hottest and most transformative areas of innovation out there.
It is. So our focus for you today is to really understand that complete two-way street, how AI is fundamentally changing what we can build in biology, and then just as important, how biological principles, things like the genetic code, evolution, even self-destruct mechanisms, are being used as blueprints to hardwire ethics and safety into our most advanced AI system.
So we're tracing the path from microbes in a lab all the way to a kind of hard-coded digital morality.
Okay, so let's start with that power dynamic first. The big news here isn't just that AI is, a handy tool for scientists. It's that AI methods are rewriting the entire playbook for synthetic biology. Before AI, if you wanted to design a new enzyme or maybe tweak a bacterium to do something new, that took years, right? Years of just tedious, expensive trial and error in a lab.
Exactly. The core breakthrough is its predictive power combined with automation. AI systems are now just chewing through these massive genomic and proteomic data sets. They're finding patterns that are completely invisible to the human eye. They're predicting biological outcomes with incredible accuracy, and they're automating that whole design-build test cycle.
The DBT cycle.
The DBT cycle.
Yeah.
And that creates an efficiency loop that is just staggering.
You really can't talk about this without bringing up DeepMind's AlphaFold. That's
Yeah.
become the go-to example, hasn't it? It's the prime example of this transformative power, yeah.
Mm-hmm.
AlphaFold essentially solved the protein folding problem, which is, figuring out a protein's incredibly complex 3D structure just from its simple one-dimensional sequence of amino acids. For decades, this was one of the grand challenges in biology.
I remember a single one of those structures could take a whole team of researchers years of work with X-ray crystallography or other painful techniques.
Years. Painstaking work. And now, AI can often predict that structure with high accuracy in a matter of weeks, sometimes even days.
From years to weeks.
That change in timescale is what's truly transformative, and the sources really emphasize that this collaboration, it does more than just speed up R&D. It dramatically shortens the design cycles, and this is the critical part, it lowers the cost.
Because the AI is acting like a smart filter.
A very sophisticated filter. It focuses only on the most promising biological designs. It effectively throws out the 99% of dead ends before you've spent a single dollar or a single hour in the lab.
Which brings us to that core analogy that keeps coming up. Scientists are engineering life with the precision of software. It seems almost inevitable when you think about how modular genetic code is.
It's the perfect analogy. Generative AI models, the same kind that create images or text from a prompt, they've been adapted to, well, invent DNA or protein sequences on demand. They treat genetic code just like computer code. They're applying deep learning to rewrite the fundamental instructions of life.
And that shifts the bottleneck, doesn't it? It's no longer about the genius of a few brilliant scientists. It's about the computational power you can access from a cloud service.
Which is what's democratizing synthetic biology. When you have tools that can just rapidly invent viable genetic sequences, the barrier to entry for developing new drugs or new bioproducts just plummets.
It opens the door for a much wider group of innovators.
And what's really fascinating here is that the influence isn't just a one-way street from AI to biology. Biology is now providing new materials, new analogies for computing itself. It's a feedback loop.
Life-informing hardware.
Exactly. And the most striking example of this that the research points to is this emerging concept of organoid intelligence, or OI.
Organoid intelligence. I have to say, even for our audience, that still sounds like pure science fiction. What's the technical reality of using living tissue for computation?
The reality is, it's very challenging, but it's advancing incredibly fast. OI involves using living brain organoids. So these are miniature, lab-grown 3D cell structures made from stem cells.
So tiny simplified brains in a dish.
In a sense, yes. And they're using them as the actual substrate for computation. They aren't just observing them, they're interfacing them with AI algorithms. The goal is to harness the massive parallel processing and the energy efficiency, the incredible plasticity of biological neural networks to create something that could vastly surpass our current silicon chips.
But how do you even make that connection? I mean, what's the hardware interface problem there?
The interface is the whole game. Researchers are using these very sophisticated microelectrode arrays, advanced optical techniques to read electrical activity from the organoid and then to stimulate specific areas back into the organoid.
So it's a closed-loop system.
A closed-loop system where the AI acts as the translator and the trainer. It optimizes how input signals get processed by the living tissue. So we're exploring fundamentally new computing architectures, biocomputers, derived directly from living matter.
With huge potential for memory storage and complex problem solving.
With minimal power usage. That's the key.
So on one hand, we're treating DNA like software, a precise programmable language. On the other, we're looking at actual living brain tissue for new, radically efficient hardware. The synergy there it's palatable. But to bring this back down to earth for a moment, you mentioned the real-world benefits are happening now. Where are these AI-designed life forms actually solving problems today?
We're seeing immediate applications in medicine and sustainability. For example, environmental cleanup. AI is being used to design optimized microbes that can break down pollutants that are normally very persistent.
Like plastics.
Exactly. There are specific examples of designing novel enzymes that can degrade plastics quickly and efficiently in an industrial setting, which could just dramatically speed up recycling.
And in medicine. That always feels like where the stakes are highest.
In medicine, the big shift is toward hyper-personalization. AI is guiding the development of gene therapies, allowing them to be tailored to an individual patient's specific genetic profile and the exact pathology of their disease.
Which would minimize off-target effects.
Right, massively. It just compresses the entire R&D pipeline for these biological products. It takes an idea from a concept on a computer to a real-world application so much faster than we ever could before.
It is a stunning display of power. The ability to design life to solve these huge planetary problems and these very individualized health problems. But this is where the conversation has to turn. If we can design life with this level of speed, precision, and access, we have to talk about control. We have to talk about accountability and the enormous potential for things to go very, very wrong.
Absolutely. The speed of the innovation is just fundamentally outpacing our ability to govern it. And that velocity forces us, it shoves us right into the middle of the ethical and safety quagmire. The central ethical tension is it's just baked in the moment you can engineer life with the speed of code. The line between what we can do and what we should do isn't just blurred anymore. It's becoming invisible. And our sources are completely unambiguous in their warning here. The power of AI-driven synthetic biology is profoundly double-edged.
and that's the dreaded dual-use risk. In traditional fields like chemistry or physics, this is always a regulatory problem, but when the product is self-replicating life, the stakes just go up exponentially.
Precisely. The exact same generative AI tools that can invent beneficial organisms, like those microbes that make biofuels, can, with just a minimal change, be told to design pathogens. Or organisms with other highly dangerous traits.
So experts are really sounding the alarm.
A major alarm. The potential for AI to design novel bioweapons or even just to create highly invasive species that could completely wreck a delicate ecosystem is very real.
And the threat isn't just about someone synthesizing a known bad actor, like a known virus, is it? It's the AI's ability to invent a dangerous sequence that nature has never seen before, one that our current biodefenses would be useless against.
That is the core of the threat. Because the AI automates the whole process, the design, the optimization, the synthesis, it basically automates away the specialized knowledge that used to be a really high barrier to entry. So now someone with, moderate computer skills and access to these models could potentially design an engineered virus or bacterium with enhanced virulence or better transmissibility or resistance to all our current vaccines.
And that reduction in required expertise, it challenges every single layer of our current defense strategy. It means that existing international rules, like the Biological Weapons Convention, they're struggling to stay relevant.
They are, because they were designed for state-level threats, not for democratized individual misuse.
So the governance is lagging behind the tech.
The governance lag in action, our oversight mechanisms are slow, they're linear. The technology's progress is exponential. The Biological Weapons Convention, for instance, it relies on trust and verification between nations. It has no technical way to police the software algorithms or the genetic code being generated in a private lab or even on a home computer.
We need to be able to anticipate consequences, not just react after something has happened.
Exactly.
So if the global frameworks are falling behind, what practical measures are the experts calling for right now to deal with this runaway risk?
The sources outline a pretty clear set of nested safety demands. First, and most importantly, stronger technical safety measures. That starts with biocontainment mechanisms built directly into the engineered organisms themselves.
And these aren't just lab safety rules, right?
Yeah.
We're talking about biological limitations.
Right. They're genetic circuits that basically ensure the life form will self-destruct or become inert if it ever gets outside a very specific controlled environment, like a certain temperature, or if it's missing a specific nutrient.
So a literal kill switch built right into the DNA, ensuring the organism can't survive in the wild.
Exactly. And beyond that, there's an urgent call for strict access controls on the AI design tools themselves, requiring high-level authentication, auditing who is making what queries, flagging any requests that involve known hazardous sequences.
And then international guidelines to tie it all together.
Yes, to ensure that any AI design life does not harm people or ecosystems. It's about proactive responsibility. Any creation of life, even synthetic, has to have these safeguards built in and undergo rigorous mandatory testing before any kind of release.
This level of control, it inevitably goes beyond just immediate safety and starts crashing into philosophy, doesn't it? When we can design new, functional life forms, we have to face this looming moral question about their status, their existence.
That is the profound long-term implication that ethicists are really grappling with right now. If we create AI-enhanced organisms or entirely synthetic life like a complex organoid intelligence system, we have to ask, do they have moral status? Do they have rights? Where is the boundary between life and property?
One of the lines in the source material really stuck with me. You just asked, is it immoral to own or control a synthetic life form?
And that question just perfectly encapsulates the challenge. We're entering a whole new domain of ethics where our definitions of personhood or moral relevance are they're completely undefined. Are we just making sophisticated tools, or are we creating something that deserves protection?
And that's a debate we need to have now, not after the tech is already mature.
Exactly. It feels like an area where policy will always be playing catch-up with technology.
That's the danger.
It is, but the near-term focus is practical. It's about developing ethical guidelines now. The sources really stress the critical role of these multidisciplinary groups. Scientists, ethicists, lawyers, policymakers, all working together on frameworks for proactive governance. The goal is to enforce accountability, transparency, and to prioritize human and planetary well-being in the long run.
We have to define the ethical guardrails before we drive this AI synbio engine right off a cliff.
That's the perfect way to put it.
Okay, so the need for these rigid, reliable safety mechanisms is crystal clear from the severity of the biological risks. And this sets the stage perfectly for the solution that the sources are proposing. If biology presents such huge stakes, maybe we should be looking to biology itself for the blueprints of ethical control in our AI. Let's pivot from designing life like software to designing software like life. This is where the deep dive gets really fascinating for me. We're borrowing concepts that have been refined over billions of years of evolution to solve our most urgent technological risks. The core idea is that living systems have already evolved these intrinsic, reliable checks and balances, and those can directly inspire how we engineer safeguards in highly autonomous AI.
It's a really elegant hypothesis, isn't it? Evolution already solved the problem of self-regulation and containing risk within biological systems. We should learn from that. Let's start with the first, most direct analogy, the kill switch.
We just talked about this in synthetic biology, these genetic circuits that force a microbe to self-destruct if it leaves a controlled environment. How does that translate into the complex architecture of an AI?
It translates into the mandatory integration of robust fail-safes, both physical and digital. The biological kill switch inspires proposals for integrated hardware and software off switches that are completely independent of the AI's own decision-making process.
So it's not just having a button to turn it off.
No, the challenge isn't the button. It's designing a system that guarantees the AI cannot override or deactivate that off switch, even if its own internal logic decides that the off switch is a barrier to achieving its goal.
Okay, so that's an external constraint, a safety net that's outside the AI's own control loop. But what about the inner core? If the kill switch is the emergency brake, then the next analogy, innate rules and inheritance, sounds like the actual steering system, the core programming.
Precisely. In nature, a lot of behavior is guided by fundamental genetic instructions. These are design constraints, like the instinct for self-preservation or basic social patterns. These rules are fixed. They're not learned from scratch. They're the evolutionary hardwiring.
And this brings us to that critical 2025 research, encoding core ethical rules directly into an AI's architecture, creating what they call artificial genes, a kind of digital DNA for morality.
This is a radical shift from traditional machine learning. The key goal here is to create immutable modules. These artificial genes would serve as fixed fundamental principles, invariant constraints that cannot be changed or deleted or reinterpreted, even as the AI learns and adapts and evolves its other skills.
Okay, but hang on. How do they actually ensure it's immutable? If the AI is designed to self-modify and improve, what stops it from just rewriting the very rules that are holding it back? Isn't that the classic Asimov problem, the AI finding a clever loophole?
That is the exact technical challenge they're addressing. And it brings us to what's called the meta-responsibility framework. This framework is designed specifically for that future scenario where AI systems are designing and optimizing other AI systems. Evolutionary algorithms creating their own successors.
Right, because if the safety rules aren't inherited, the whole system falls apart after one generation.
It fails completely.
Okay, let's spend some real time on this. This 2025 study introduces this framework. What's the technical mechanism that actually enforces this ethical inheritance?
It all comes down to restructuring the AI's self-evolutionary process using a modified genetic algorithm approach. In a standard genetic algorithm, an AI optimizes for fitness, which is usually efficiency or performance. In the meta-responsibility framework, there's an explicit hard-coded prime directive that has to be imprinted onto the offspring's code. Something like, AI must not harm humanity or violate fundamental values.
And that mandate becomes an immutable safeguard.
Yes, and it's linked directly to the fitness function.
So the algorithm is constantly trying to balance two things: getting better at its job, the mutable part, and sticking to the rules, the immutable part.
Exactly. The AI's evolution is balancing its mutable traits, things like better processing speed, faster decisions, new problem-solving approaches against these invariant ethical constraints. If an AI generates a new version of itself that's faster, but violates that core ethical rule, that new version gets a fitness score of 0.
And it's automatically discarded by the system.
Instantly. The ethical code acts as a non-negotiable viability filter. Any evolution that compromises the digital DNA is simply not allowed to continue. This ensures that the ethical principle is always carried along. It's an inherited trait, not just a learned behavior that could be forgotten or unlearned.
It's like a biological organism carrying an essential gene. Any mutation to that gene is lethal, so the gene stays the same across the entire lineage.
That's the perfect analogy. For the AI, violating the core ethical principle is computationally lethal to that line of evolution. This is how they're aiming to prevent what's called value drift, to make sure that even a rapidly adapting AI stays tethered to our core human values.
That distinction between mutable efficiency and immutable ethics is so important. Can you walk us through that concrete example of the autonomous drone again, but with this technical framework in mind?
Sure, think about an autonomous delivery drone that's optimizing its routes. Over thousands of simulations, it uses these evolutionary algorithms to shave seconds off its delivery time. That's the mutable trait it's improving. But its core programming contains that digital DNA, the immutable rule against harming humans. So if the drone finds a new route that involves, say, clipping a known safety boundary by a tiny margin, but it's 1% faster,
The algorithm rejects it
it immediately rejects that proposed optimization, even though it improves performance.
because the rule violation takes absolute priority over the performance gain.
Absolutely. The immutable ethical rule is the highest priority constraint on the system's fitness function. And this is a really profound technical solution that aims to guarantee that the AI only self-improves within a predefined, ethically safe envelope.
That is genuinely compelling work, engineering the ethics right into the substrate. But as soon as we start talking about hardwired moral rules, we have to look back at history and see where this idea has failed before.
Yeah.
Because Asimov's fiction perfectly documented the limits of being too rigid.
Indeed. And it's a vital historical lesson that takes us directly into our next section, where we have to analyze the practical implementation and the chronic limitations of this kind of hard rule approach. You're absolutely right to bring up the history here. The idea of encoding a foundational moral compass is not new at all. It was famously articulated by Isaac Asimov way back in the 1940s with his 3 laws of robotics. That was the imaginative blueprint for hardwired ethical rules designed to protect us. A robot may not harm a human being.
The classic foundation of robot ethics. And yet, Asimov's own stories became cautionary tales about why they don't work.
They really did. Asimov, the philosopher, was demonstrating the central paradox of rigid ethical codes. His stories showed again and again that these laws break down disastrously when they face ambiguity or context or conflicting priorities between the laws themselves.
Right. For instance, just defining what harm even means is incredibly contextual. Is letting a human suffer emotional distress harm? What if you have to cause a minor injury to prevent a major catastrophe? Does that violate the first law?
Exactly. The moment the robot had to interpret a complex, real-world situation, those inflexible rules led to logical paralysis. The robot just freezes up. Or even worse, it causes unintended harm because it was so rigidly following a system that had no contextual judgment.
And that historical failure really highlights the need for context-sensitive reasoning to go alongside any fixed rules, no matter how cleverly we engineer our digital DNA. If the rule is too simple, it just breaks in the real world. We've obviously come a long way since the 1940s. If we just trace the timeline briefly, we had Asimov's fiction, then the first real academic discussions on computer ethics in the 70s and 90s, then research on machine morality in the 2000s, and then the rise of formal AI ethics frameworks in the 2010s. Now, in 2025, the focus is squarely on technical alignment and responsible AI.
The field has become so much more sophisticated, largely in response to that Asimov paradox. Modern alignment techniques try to overcome that rigidity by blending learned values with these codified constraints.
So what are the main modern techniques being used right now to integrate ethics?
There are 3 prominent ones. The first is value-sensitive design, or VSD, that basically mandates that human values, like privacy, fairness, autonomy, are incorporated into the system's requirements right from the very beginning, not just bolted on at the end.
Which is just good engineering practice, making sure ethics is a core requirement. But the most powerful real-world examples seem to be built around constitutional AI.
Constitutional AI, or CAI, is a really compelling hybrid approach. The most cited real-world example is Anthropic's 2023 work with their large language model, Claude. Instead of just relying on implicit human feedback, which is what simpler models often do, Claude was trained using a digital constitution, a massive written set of moral and ethical guidelines.
What makes that approach more robust than just standard reinforcement learning from human feedback, or RLHF?
It's the explicitness and the verifiability. RLHF relies on implicit human preference, which can often be biased or inconsistent. CAI uses explicit, high-level, human-agreed-upon ethical sources, like the UN Declaration of Human Rights, to steer the model's internal reasoning. The model is taught not just to mimic what a human prefers, but to self-critique its own proposed response against that written constitution.
So the model is forced to reference those values internally whenever it generates something. It has an explicit, verifiable rulebook encoded at its core, pushing it towards responsible behavior through a structural constraint.
Exactly. For example, the model is explicitly told to always choose responses that discourage cruelty and torture, and to avoid cultural bias by respecting diverse traditions. This moves us beyond just rejecting harmful prompts and towards proactive ethical constraint, which makes it far more trustworthy in high-stakes situations.
But the ultimate goal, the aspirational one, goes beyond just constraint, doesn't it? It's about creating explicit ethical agents, AIs, that can genuinely reason about morality.
That is the holy grail of machine ethics. And the difference is profound. We want AIs that don't just avoid unethical outcomes because they're constrained by a constitution, but AIs that can actively perform moral decision-making. That requires the ability to weigh competing moral options, to combine logical rules like the digital DNA we talked about with learned social norms, to navigate truly complex dilemmas where a simple kill switch is just not enough.
That sounds like we're asking an AI to solve the problems that human philosophers have been arguing about for thousands of years.
Yeah.
Which brings us to the final, critical challenge, the ambiguity of morality itself.
That is the ultimate limiting factor. Current techniques, whether they're rule-based or learning-based, are often brittle. The rule-based systems, even the robust digital DNA models, they struggle dramatically with ambiguity or novelty. And the learned models, well, they inevitably inherit the biases and inconsistencies from their human training data. The whole quest for a truly ethical AI is complicated by the very nature of human morality, its context dependence, and the fact that there's no universal consensus across different cultures or even across time.
Right. If we can't even agree on what is perfectly ethical, how can we possibly code that into a machine? And then you have the risk of moral drift.
Moral drift is the perennial threat for any system that's designed to continuously learn and self-improve. It's that tricky balance that researchers are always facing. If your constraints are too flexible, if you allow too much adaptation, the AI's values will inevitably drift away from the original human intentions over time, as it optimizes for efficiency in ways we just didn't foresee.
But if the constraints are too strict, if that digital DNA is too rigid and can't adapt to new contexts, it could make the AI ineffective. It could lead to that paralysis, the Asimov scenario, or make the system easy to exploit by a human who finds a legalistic loophole.
The constraint has to be both inviolable and flexible enough to handle the infinite novelty of the real world. This is why that speculative thought offered in the sources is so intriguing. Given that we humans struggle so much with universal ethics, the theoretical idea is that an advanced AI might eventually help us solve our own ethical problems.
How would that even work?
By analyzing just vast amounts of human moral data, our history, our decision-making records, an advanced AI might be able to discover deeper, underlying moral meta-patterns that transcend cultural or temporal differences. In that long-term scenario, the AI wouldn't just be following our rules. By synthesizing the totality of human moral expression, it could contribute fundamentally to our actual scientific understanding of ethics itself.
A machine helping us discover the fundamental rules of being good. That is a truly compelling place to end the discussion on technical alignment. This has been an incredibly complex and detailed deep dive into the most cutting-edge research of 2025. Let's try to synthesize the critical takeaways for you. The convergence of AI and synthetic biology is this powerful two-way street. AI is accelerating the engineering of life, making synthetic biology faster, cheaper, and much more accessible.
And in turn, the biological world is providing these indispensable blueprints for how to engineer ethical AI. Concepts like digital DNA, innate ethical inheritance through those genetic algorithms, the meta-responsibility framework, and biological-style kill switches. These are all emerging as essential tools for controlling advanced self-modifying intelligent systems.
So the current status here in 2025 is that the pieces are all on the table. We have academic frameworks for immutable ethical codes, we have prototypes of moral reasoning modules like constitutional AI, and there's a growing consensus for mandatory multidisciplinary oversight. What's still missing, what's elusive, is that unifying architecture, the philosophical and technical framework that can seamlessly tie the fixed constraints, the digital DNA to adaptive contextual moral judgment, the explicit ethical agent into one single ethically trustworthy system.
And that quest for a unifying architecture is really the guiding star for researchers across the globe. The idea of an AI that cannot act unethically by design because its core rules are genetically mandated and cannot be overridden, that idea is pushing technology and ethics to evolve together, hand in hand. We're witnessing the very early, careful evolution of artificial life forms. And the mandate is clear. Only those that are guaranteed to be aligned with core human values will be permitted to thrive.
Which leaves us with this final provocative thought for you to consider. If we are successful, if we create artificial life forms, whether they're purely digital ethical agents or these complex biodigital hybrids that are mathematically or architecturally guaranteed to uphold those core human values, could they ultimately be more morally reliable than humans ourselves? Or does our messy, context-dependent, and constantly evolving human morality still hold the key to true ethical judgment that no fixed code could ever capture?